Thank you very much. Thanks for the introduction and the invitation. So yeah, I think Patrick summed it up. My interests are very broad. In general, they are in the area of the application of artificial intelligence to enable robots to be more effective, more flexible, more reliable, more robust. And we've done, in our lab, we've done things all across that spectrum, from real kind of industrial applications in logistics robots to kind of very blue skies applications of robots talking to humans about toys and things like that. So given sort of the breadth of my interests, given the sort of purpose of this as a training event in a way to get you all thinking, in the early stages of your PhDs, hopefully thinking more broadly about the world, I'm going to give a kind of broad talk. So I'm going to cover a range of different examples of learning and knowledge that have interested me in the last sort of 3 or 4 years. And it's purposely just really to give you a taste of some different areas where different knowledge representations have been used, different machine learning techniques have been used, and all for slightly different applications. So the aim here is really just to give you a taste of lots of different things and show you how techniques can be used to solve particular problems without really drilling down into the details of any individual problem. I'm very happy to take questions as we go along. Patrick warned me that you're all a bit quiet, so please prove him wrong by either asking questions as we go, so just stick your hand up or shout out, or save them to the end, so I'll make sure there's time at the end for some questions. I should also say I've probably put way too much content into the talk, so I will take the really professional approach of just randomly skipping slides as we get near the end. Also, if I speak too fast or my English isn't clear, again, stop me, because the aim of this is for you to all hopefully get something out of the talk. So yeah, please interrupt. So, although I said I'm going to do sort of quite a broad range of examples, they're all going to be inspired by one sort of application or one dream, which is the ability to use autonomous robots for long periods, so weeks or months or years, autonomously in everyday environments. So I'm really interested in putting robots in environments like this, so supermarkets, homes, warehouses, hospitals, places where there are challenging dynamics, places where we can't control the world, and places where the robots have to adapt over long periods as they work there. So we can't go in and model the entire environment and then let our robot loose. The robot has to learn and adapt as it goes over long, long periods of time. So this is work that we've been sort of approaching in an EU project called Strands over the last almost 4 years now, something that Patrick and KTH have been part of, and something that a range of other collaborators have contributed to. And the work I'm going to present here is joint work with all of these universities in varying amounts and for varying purposes. So this is very much kind of joint and broad work, and if you end up working in the area of AI applied to robots, you'll necessarily have to be broad, because one of the interesting things for me about that area is you have to be able to work from the very, very low level with sensors and effectors all the way up to abstract, symbolic, and semantic knowledge. And in fact, the semantic knowledge is really the way where we've been targeting in Strands, to try and abstract up from the messy, noisy, low-level details of robots and control up to some structured semantic representations that the robot can use to reason about its world over longer periods of time. So that's the target. We've made kind of baby steps in that direction. And I'll give you, to start with, some examples of the kinds of robots we use and the kinds of application domains we've been working on, only to sort of cruelly take away the robot videos and then start showing you graphs and maths. But this is kind of the sort of deployments we've been working on, and the robots we've been working on. So up here in the top right-hand corner, you can see Bob. Bob is a Metrolab Cytos robot. We've got one at every partner. And we've been putting these robots into end-user environments like this one, which is G4S Technology in the UK, so a security company, and working on a range of tasks: observation, monitoring, facilities management, security checking, assistance in care, these kinds of things what our robots have been doing. But the key thing for us is these robots have been running autonomously, so under their own steam, with no human control, or no expert human control, for long periods of time. So this deployment lasted 35 days. We took the robot there, we got it running, we all left. Then it was down to the end users who were actually working with the robot to pull it out of corners and make sure it didn't get stuck. And that included what we think is the longest on-record autonomous deployment, kind of continuous autonomous run in these environments of this complexity, which was 28 days, the robot, without any unrequested expert intervention. So the robot, didn't completely power off. It didn't get calamitously stuck and run out of batteries. And there was no major software bugs. So the robot was actually able to autonomously perform for 28 days, which is really exciting. Recently, we've been at a place called the Transport Systems Catapult in Milton Keynes, this time with the yellow robot, that's Betty. You have to name your robots. That should have been lecture 1 on this graduate course, I think, how to name robots effectively. And again, we're doing driving around in dynamic environments. We're tackling really scary obstacles like doors, and generally big glass walls. So this is not a place you ever really want to take a mobile robot. But equally, we're working with users, we're dealing with the dynamics, we're learning over long periods of time. And the reason I kind of bring this up at the start is because when we're talking about learning and knowledge representation, reasoning, actually it's the data, it's the knowledge that's important. So these robots are, in some cases, learning online. So we're doing some online adaptation and optimization, but we're also gathering large data sets which we can work with in machine learning tools and reasoning. For example, in the top left here, the robot is doing a meta-room scan, which means it's scanning 360 degrees, a couple of levels, and producing a big merged point cloud. We've got all of that data saved, and it's publicly available, most of it. So if you're doing a PhD and you'd like some data from mobile robots over long periods in indoor environments, please drop me an email or talk to Patrick, and we can give you access to all sorts of exciting data from here. OK, so I'm going to talk on sort of 2 broad strands of research. The first strand will be talking about objects, because objects are very important for service robots. Humans care about objects. They want robots to move them around and understand them. And so I'll start talking about objects. Then after that, I'll talk about people and how they move and how we can learn about that from a mobile robot as well. OK, so object detection is something we've had a horrific time with, to be perfectly honest. Early on in the project, we tried to take some off-the-shelf 3D categorization components and run them effectively without too many modifications on our robot. You can see the results here. There's lots of lessons to be learned from that deployment, including don't trust computer vision people when they say it works. It almost doesn't. But also, there's lots of interesting interactions between your sensors, your algorithms, and your robot. So effectively, where do you position your robot to get the most out of your sensors and your algorithms jointly? That's not something I'm going to talk about today, but instead I'm going to sort of talk about a flow of work that we've been pursuing that tries to avoid the traditional computer vision approach of building a very complex model from lots and lots of data and then labeling it exactly and cleaning it up. Because those models for us don't ever seem to work, largely because when you put them on a robot, the inputs the robot gets, which is very noisy depth clouds, it's very strange angles of objects, those are not accurately kind of addressed, I think, by the standard computer vision literature. So we've been working on a pipeline that goes from object discovery through to labeling, through to recognition, and I'm going to talk about each of those steps a little bit now. So the first thing we want our robot to do is find some objects in the environment to know about. So in the kind of traditional world, you build models of objects before you go into a site. So for the Milton Keynes, the Transport Systems Catapult deployment, it took us about a day to build models of about 8 objects accurately, which is really, really inefficient given there are hundreds and hundreds of different objects that the robot might need to know about in that setting. So instead of training the robot manually, we wanted the robot to discover objects that it could know about. So to do that, what we've done is used change-based segmentation. So again, we do these meta rooms. So at the top up here, what you can see is the robot stitching together point clouds from lots of different angles. This is the kitchen at KTH, and this is their robot, Rosie, scanning around, taking these images. Now, here, the long term is of interest. So in our deployments, the robots do this every day, multiple times at the same location for multiple locations across a site. This gives it lots of data that it can use to accurately stitch together and register the point clouds, but equally it allows the robots to build up a model of what changes and what doesn't. So this gives us the ability to have a very good, dense model of the static structure of the environment, And then when we do a scan like this one, we can detect what has changed between the static structure and the currently observed structure. If something changes, then the robot should know about it, and that becomes an object that the robot is curious about. So what happens? The robot discovers that something's changed, and then it can drive around taking images of that object and building a 3D model. So instead of having a human put an object on a turntable or get really close with a Kinect, we're gathering an object model from a kind of a realistic range and with realistic sensors from the mobile robot. In this case, we're using a controlled setup where there's a microwave placed in the middle of a room, which is, of course, an unusual place to find a microwave. I assume it's unusual in Sweden. OK, this isn't a standard setup. And what we're doing here is running short-term visual SLAM to stitch together the separate images you see here, and making some assumptions about the shape of the object, the local smoothness. And from that, we can create a model of the object in 3D. In this case, we can see every side of it. But in the general case, when the object is sat on a desk or something, we don't get to actually see that much. So what you can see here is the evaluation we did in the paper, where we put some objects which we had ground truth for into everyday scenes. And these are the objects that we found on desks. So in this case, that sounds good to me. Is that all right for you lot? Yes, thumbs up at the back. In the middle, we had a kind of a middle case where we put the object on that table in the middle of the kitchen, and so we got to see all sides of it. So this demonstrates that we can automatically build these object models from autonomous discovery. In the middle cases, we're cheating by kind of putting it on a nice, friendly surface. In the bottom cases, we're burying it in clutter on Patrick's desk, so it's a bit more challenging to find. But this just demonstrates that we can do it, and you don't need to go through elaborate modeling steps to get these objects, provided they're of a certain size and move in the environment. What you see at the top are graphs of recognition versus completeness. So as you move, let's use the example on the far right, as you go from 0 to 1 on the x-axis, we're getting a more complete model, and that completeness is measured against the ground truth. And as you go 0 to 1, you see the F-score, so the reliability of recognition, effectively, of that model. So as you get more coverage, you're more able to recognize it. The shapes here give you points that correspond to the models we built in the uncontrolled setting. So these are not always very well covered. So in the case of this box, all of the uncontrolled settings, we only saw a small fraction of the object, and that shows that we're correspondingly only able to recognize it a small fraction of times. But overall, we're actually able now to discover objects in our environments. We've run this for 2 years in our long-term deployments, and this is where the lessons of real-world robotics come in. The first year, our camera calibration was completely off, so the robot spent time trying to learn objects. So if it was trying to learn this mug, this cup, it localized the cup and then spent all the time looking about 50 centimeters lower as it tracked around the surface, which was very frustrating. So we got loads and loads of data full of nothing. In the second deployment, everything worked according to plan, but the place was dominated by people. There was loads and loads of people. So what would happen is when the robot did the meta room and segmented the clusters that had moved, most of those clusters were people. So from the last year's deployment, we've got 60 days of the upper bodies of very grumpy-looking people because they're sitting there trying to work, and the robot is coming around their head. So doing real-world robotics, there's lots of kind of social elements too, which is very interesting. So let's just summarize that bit. I'm going to try and do this again in the teaching kind of part of it to sort of give you a sense, just to summarize the different bits, because otherwise it's quite a scattered shot presentation. So in this case, what did we learn? Well, we learned 3D object models from a mobile robot. That's interesting because usually those things have to be hand-coded or built manually. So we're autonomously learning 3D object models. How do we do it? Well, this isn't machine learning as such. We've got a pipeline where we stitch together a range of things we know that work. So doing the change-based segmentation, then short-term visual SLAM to allow us to know how the different views of the object map together. And then we were able to use that to re-recognize objects in realistic settings. So I should say, even though I described failures in the long-term use of this system, even though we were kind of learning junk, we could re-recognize that junk in everyday scenes, as useful as that is. And again, I recommend, if you want to know more, there's a paper with the full evaluation, the full pipeline, and the algorithms we used. So this is
a good place to start. We can learn some object models. But in general, if we want to get up to this semantic level of understanding what objects are in the world and describing them, we need to have some sort of notion of what those objects are. Now, the problem is we don't know what those objects are. We don't know what the robot has learned. And the robot doesn't know what it's learned. It's just got a 3D chunk of voxels, right? It's got a bunch of voxels of different colors and different shapes. How is it supposed to know what that is? So what we've been doing is we've built a web interface that runs on site where the robot is. When the robot produces a new object looking like this, so this is the front side of a med kit, along with the image one of the images that was used to generate it. And this isn't faked. These things are all over Transport Systems Catapult. I guess they're very injury prone or something. And what we'd like to do is we'd like to give the human annotator some suggestions of what the object might be, so the human can pick a label and enter the label just by clicking on a button. So that speeds up the labeling process rather than having them to have to kind of decide themselves what it is. So one of the advantages of that, yep. That's the next bit of the talk. So the question was, where do we get the labels from? And I will get onto that. So we'd like to give the human some labels. This is an awful example of labels, and you'll understand why these are awful suggestions when you see the method we're taking, which isn't awful, but in this case doesn't work very well. We'd like the human to be able to select from a range of labels because we want to narrow down the range of things they could say are there, instead of them saying, oh, this is Trevor's med kit that he got last week, which isn't very useful for the robot's perspective. We just like to get med kit. So we want to have some way of constraining the human. But this raises the question of, given the robot has never seen these objects before, how can we recognize what they are? How can we even produce a couple of suggestions for a label? So the clue is in that picture. Does anyone want to suggest a way we could kind of perhaps present some labels to the human? What kind of general approach, what kind of general source of information can we use to suggest some labels there? Someone give me an answer. Oh, yes, at the back. Google? Close, actually. Another more general, or more thinking of as AI people, thinking as scientists. What is in this that we can exploit? Yep. Yep, so what can you usually find on a desktop? What can you usually find next to each other? The key here is that, for example, desktops all look the same, at some level of abstraction. When you go around and look at desks, or you go around and look at different bits of an office at the same time, there are similar patterns, okay? There are similar patterns which we refer to as context. The context in which you find an object helps you determine what it is, even if you've never seen it before. So there are two types of context that I'm going to talk about. Spatial context, so where you find something and how they're arranged, and semantic context, which is really what do I find it with. So they're very similar because often you find it with things in a particular arrangement, but we've tackled those two things, well, we've tackled them together, but I'm going to break them down separately for you. So the aim here is to try and produce some set of reasonable labels for an unknown object, given we've got some observations about the things that it's near and the things that we see it with. So the first question for the semantic context is, how are we going to define the semantics or the meaning of an individual entity? In general, what people do in AI is they use sort of symbol systems or ontologies where you've got a rich and formalized logical understanding of an entity. If I had a model of a mug, I would have a conceptual hierarchy in which the mug is a sub-element of drinking vessel, which is a sub-element of utility vessel or something, which is kitchen item, which is object, which is thing. And I've got a very rich kind of ontology. The problem with that is it's quite brittle and not always hugely scalable in terms of content. So someone has to generate that content manually, typically. So because we're dealing with unknown objects, we want a system that can represent hundreds or thousands of different objects, and we can manipulate that representation quickly to find similar objects to the things we're looking at. So here we're interested in scale, the ability to see, or to reason about thousands, hundreds of thousands of objects quickly, and to also have that breadth of knowledge. So in this work, we used something called distributional semantics, which is a topic from natural language where the meaning of any entity is defined, or defined it by the co-occurrence of other concepts you find it with. So if I had written if I had a textbook about looking after a dog, that book would have the word dog co-occurring with vet and insurance and, poo and food and walks and garden or something. And if I had a textbook about keeping cats, they would have a similar list of co-occurrences. The word cat would occur with vet, and the would occur with food and insurance and sofa and things like that. And then what I can see, if I see that cat and dog co-occur with the same set of words in similar frequencies, I can say that cat and dog are somehow semantically similar. So I know a cat is not a dog, but I also know that they appear in the similar semantic context, so I can say there's something similar about cat and dog. So that means that if I have an observation of a thing, I don't know what it is, but I know it co-occurs with insurance and vet and sofa, well, I can say whatever I've got is similar to a cat and a dog. So that's the general idea we're taking. In this case, distributional semantics, you produce things called entity vectors. The entity is the thing we care about. A vector is this, in this case, in a machine learning sense, a list of features. And the features here are co-occurrence counts over a corpus, so a big database of documents. So, for example, you could look at all the answers to Stack Overflow questions. In our case, we looked at Wikipedia and did the co-occurrence counting on Wikipedia. Or in fact, someone else did the co-occurrence counting on Wikipedia. That gives you a co-occurrence matrix. So in this case, we found washing machine and bathroom together, which means we get an extra increment in our washing machine and bathroom entry there. And then because this produces a huge, possibly redundant co-occurrence matrix, we run some dimensionality reduction on that matrix, singular value decomposition, low rank approximation, types of PCA, things like that, to get rid of the stuff that doesn't have very much information in it in the matrix and keep stuff that is. So hopefully you've got this picture now of a long vector with counts for insurance, vet, kitchen, whatever. So then for a particular item, you get a particular vector. The approach we're taking here is called Nassari, which is the work of these people here. And what they've done is they've processed the whole of DBpedia. DBpedia is a mapping is an extraction of concepts from Wikipedia, but annotated with semantic linked data contents, i.e. this ID is a unique ID for bathroom. And then all the numbers after it are the result of dimensionality reduction to describe the bathroom concept as a vector, this case vector meaning a line with an orientation and a magnitude, so a vector in high dimensional space. So bathroom is an arrow in high dimensional space, and you can get all of these concepts from this link. And we have multiple concepts, so bathroom and washing machine. And because we want to care about how similar they are, so again, we were caring about how similar washing machine and bathroom are, we look at the similarity of those lines, of those angles in high dimensional space. So to do that, we use cosine similarity, but of course it's easier to have a picture. So cosine similarity in 2 dimensions is saying how similar are these, roughly, are the angles between these vectors. So washing machine and bathroom might have vectors like this. There's an angle between those vectors here in 2D, but in this general case, in multiple dimensions. And we can compute the cosine similarity, which gives us a number. We can do the same for bathroom and ashtray, which gives us a smaller number. So we can say that bathroom and washing machine are more similar than bathroom and ashtray. Doesn't necessarily make any sense to think about these in absolute terms, but think of them in relative terms. What is more similar or less similar? So in this way, we can take an arbitrary concept and compute its similarity with some other concept. Okay? So to put this into a system, we link this somewhere in the middle. We start with robot vision. So the robot looks at a scene, again from one of these meta-room sweeps, or from a more directed object search process, does some segmentation, feature extraction, and labeling, and maybe recognizes a few things. So in this case, we can recognize the monitor, we can recognize a mouse, and a few other things. We can also recognize, for example, the surface that the object is on. We have some good semantic segmentation work in the project that can really well identify desks, kitchen worktops, coffee tables, things like that. We also know with quite high confidence what kind of room we're in. So we might know we're in an office, we might know we're in a kitchen, we might know we're in a meeting room. So what we do is we take the list of things we've observed the unknown object with. Okay, so we've got these things we know, that it's in an office, that it's next to a mouse, that it's next to a monitor. And then we've got a world of possible objects, or a universe of possible objects. So this is a long list of things that we think might occur in our environment. So there we just write down every object that we ever think the robot might see. Okay, quite a long-winded process, but you can do that automatically from looking at a concept tree which has, say, office item, and then you just expand the tree underneath and just use all those objects. You know, office item, kitchen item, bathroom item, gives you a list of all the items from Wikipedia that are listed there. And then what we do is we take the list of known things about our observation of the world, and one by one, we compute the similarity, the sum of the similarities over our known things with every item in our universe of objects. So this is why we want something that's fast, because if that list is really long, it's going to take us a very long time to do the computation. We can do it in parallel, which is good, but in this vector case, we're just doing, computing that equation for every object in our world. If we do that, we can end up with a ranking of objects from our universe of objects based on their combined similarity to the observed objects. So in this case, for where we know there's a monitor and a mouse and a phone or something, the ranking that we get out is input device, light pen, touchpad, trackball, and text entry interface. The thing we didn't know in this case was a keyboard. So text entry interface is probably pretty good, and input device is pretty good. But this also shows you some of the problems with working with automatically generated concepts and concept trees. You've got no way of controlling what level of hierarchy you get. So one of our favorite things in the project, I should have included a picture, is there is a concept in Wikipedia for jug shaped like a head, which is a very, very specific thing. The likelihood of you ever finding that is quite low, but it will exist in our universe of possible objects. It's probably too specific to ever be useful, whereas jug is quite a useful concept. So if we do this, we take our known objects, we take our list of possible objects, and we rank each possible object by the combined similarity to the known objects, and we end up with a ranking that tells us the things that we should suggest as labels for the unknown object. This is the reason why the labels for the medkit were terrible, because the medkit was just dropped on the end of someone's desk. So it has to be at certain places throughout this office, which means they're left in office-like places. So the suggestions for it were based on the context, which was, in fact, if we go back, let's see what the suggestions for kind of office-type objects were. Pencil sharpener, desk, eraser, notebook, hole punch, paper size. So these labels come out of our system. It's never of course, there's one weird one, lazy Susan. There's always one weird one. But this shows you, this is very prone to knowing about the context that's there. It's very dependent on what you observe and where you observe it. If you observe, and this is true for a lot of knowledge-based robotics methods, if your world doesn't match your underlying assumed distribution of concepts and objects, you're suddenly looking really, really stupid, as in this case. So we do this, and what we did is we did this for a range of data sets. So we've got 2 object data sets. In this case, we're looking at objects that the robot saw during its deployment in Milton Keynes, the 60-day deployment. And down the left is the ground truth. So this is what the robot actually saw. And what we're doing is we're scoring the similarity between the top-ranked suggestion, so the best suggestion, and the ground truth. In this case, we're not measuring exact match, because that's all or nothing. And the chance of getting an exact match is very low. We're using something called the WUP similarity, which is a WordNet measure of similarity. WordNet is a collection of words grouped into synsets into a categorical hierarchy. And what we do, what similarity does, and it's a very old measure, is it measures the closeness of the 2 concepts in the tree relative to some higher level concept that subsumes both of them. And it also looks at the depth in the tree. So if you are high up in the tree under a common subsumer, it generally means you're more similar because you're closer in the tree. So if this is kitchen item up here, then the two things under the tree, if they're just one hop down on either side, if we've got knife and then fork, and maybe this is cutlery and we've got knife and fork, they're very, very similar. If this is knife and bread bin, and the common category further up is kitchen item rather than cutlery, then you can see they're much further away. So this is the measure we're using. If you get a score of 1, it means you've suggested the exact thing. If you get a score of 0, I don't think you can get a score of 0, actually. So you can get a score of very, very low. It means you're about as far away in this concept tree from between the two concepts as you can possibly get. So what you can see is in some cases we do reasonably well. Cup, glass, bottle, we're typically observing them in the kitchen, so the context works well. Down here, things like duct tape, we have very bad predictions for. Scissors are tough because I think we find them everywhere. Banana scores low. It's interesting to think about why banana scores low. It's because bananas are found everywhere, right, in offices. But there's no reliable context for identifying one, right? Bananas are in kitchens, bananas are in desks, bananas are near waste bins, because people eat them as they go around and they do stuff. Whereas our semantics are drawn from Wikipedia. So any mention of Wikipedia, the mentions of bananas in Wikipedia are more about the categorical knowledge of what a banana. Banana is a fruit, a banana is found in these countries, a banana is a staple income of a particular country. So therefore, the predictions we have on spatial context are not so good for the semantics in this case. Yep. Yeah, but the key here is we're using information about where they're found as well. So in our set of observations that we use to draw the inference of similarity, we're including things like the room type. So I think here you get quite easily to kitchens, washing up bottles, kitchens drinking bottles. So whilst they're found everywhere, in our robots world, it's finding them in the places that Wikipedia knows about or can draw quite close connections to. Whereas the knowledge, the semantics encoded, the distributional semantics encoded in Wikipedia don't have office observations of bananas very prominently. Yep. Sorry, say that again, between the vector and the... Okay, the concept tree is how we're evaluating it. So WordNet is a tree of concepts where you start with very, very abstract concepts and you can link them together and you have more specific concepts coming off that. So you've kind of got an ontology of connected concepts. And in each node of this graph, effectively, there are lots of words that mean the same thing. So they're called synsets. If, in our prediction task, if the ground truth is one thing and our suggestion is one thing, and they're in the same node of the graph, you get a score of 1. Effectively, the further apart they are in the graph, the lower score we get. Because the further apart they are in the graph, the less similar they are. But this scoring system is biased such that if we suggest this, and the answer is a child, kind of a closely related child of that, they're semantically quite similar, so we still get a decent score. If they're both very separate under different parents in the tree, we get a very low score. So it's kind of a graph distance measure that takes into account that this graph has certain properties. Cool. This graph, I think, is manually generated. So if you look at WordNet, there's lots of papers on it and how it's generated. My gut feeling is it's manually generated. These are all great questions. Keep them coming. You were wrong, Patrick. They're not quiet. Yes? I think that's one for the natural language researchers. So I know very little about that part of it. It's a tool we use. But there's tons and tons of... It's one of these communities where everyone has a slightly different view on, how you should dimensionality reduce the vector and how you should count the windows of counting and things like that. So there's tons of literature on that. Yep.
Are you using label data in the labeling of new targets? Like if you have labeled a cup, you might be able to use that knowledge in labeling another cup, looking quite different.
Yeah, so the question was, are we using old data to label new data? So if we'd successfully labeled a cup in an old setting, can we use it to relabel a new setting? So we haven't done that, but we'd love to do that. It's a great idea. You could actually use reinforcement learning or something like that to look at the state space of choices you're making compared to your observations and choose different things every time, because we have maybe 8 or 10 humans that are looking at these labels. So we can use some learning approach to look at what labels we suggest versus which ones they choose versus what we're using to make that decision. So it's a great idea, and it's something we'd like to do in the future. Cool. Right. So this isn't the end of the story, because we thought, well, what other techniques exist right now that help us label, that could label hundreds or thousands of object images for us without having a detailed training model? So what could we use for that? Any ideas? What other techniques, given that we've got images that we could use to label thousands of different images quite cheaply nowadays? Deep nets. Yes. So there are tons of images, deep nets that are trained on ImageNet. The great thing about ImageNet is every image in ImageNet is mapped to a category in WordNet. So we automatically have the grounding into our conceptual hierarchy for our labeling system, and you can go and download networks that are trained on ImageNet and run them on this data. So this is stuff, so what I've shown so far is in published work. What I'll talk about now is in our current IROS submission. So we tried it. We tried an off-the-shelf deep net, which I can't remember which one, I'm afraid, on the same data, and we got interesting results. The interesting results is deep nets don't solve everything. So in some cases where vision typically struggles, we do a lot worse using the CNN, using the deep net. In some cases, we do better. So up here, for bottle, we're better at spotting bottles. Oh no, hang on, the wrong way around. Yeah, no. What color is green is vision. So in these cases, laptop, we're much better at spotting things with vision. So as new scientists, you should look at that and get excited, because clearly they're both performing differently. They're both exploiting different things. And so the kind of question you should have is, what happens if we add them together? And that's what we've done recently in a relatively ad hoc manner. But to give you an example of how it works, we take an image, and what we do is we get the context. So the context suggestions for this image are related to where you find it and what you do with it. So it's kitchen, it's cooking. So coffee, toaster, oven, plate, Pyrex. So Pyrex is a type of bowl for those of you that don't do cooking. Or it's a type of glass that you use to make cooking bowls. Vision predicts things that look similar. So crate, safe, microwave, refrigerator, and fire screen. So boxy, rectangular things. What we do in this case is we rank or kind of filter the vision based on the similarity to the context. So we go through each item in vision and score the similarity versus the context. So we know that context is somehow more constrained to the space that the robot's in than the vision. But the vision has a kind of broader acceptance of everything. So it's not, it's able to see stuff perhaps more specific to type. So in this case, and this is a real example from our data set, we can find things like microwave and refrigerator are very similar to the things that appear in the context list, whereas crate and safe and fire screen are not similar to the things that appear in the context list. Now, if we put those together, we can take the best ranked solutions then from vision suggestions and suggest those to the human. In this case, microwave becomes the top suggestion. So if you combine vision and context and semantics, you get a better prediction. So if you take the graph we saw previously and we add in the joint system, we get this really pleasing line in which in almost every case, the joint system outperforms the individual components. What this tells you is vision is actually pretty good, but it's not always good at getting the first thing right. It means it's often getting stuff quite high up in the list that's right, but it doesn't know that it's the right thing, whereas we can use the context to boost the vision answer up the list. So in the case of the top two, glass and cup, we get 100%, we get the right suggestion first time. We're still at the very bottom. For banana, we're not doing very well in any case, which is interesting. So it's the same answer. So in both cases, mobile phone will be far down the list. But now, if it's effectively just random entries, then there's going to be there's going to be very low similarity. So if you imagine every entry is random, you've got random entries in both graphs, the similarity should be very low, because they're probably going to be a decent distance away, the average distance in the tree. If you just get one thing in each one that's similar, then that means they're going to be very close in the tree. And the probability of getting two things close in the tree is quite low if everything's random. So that means the similarity there jumps them up the list. Does that make sense? Vaguely. Yes? So yeah, all of them give us confidence levels. We're not really using them yet. Currently what we're doing is we're basically thresholding the vision result above a certain semantic confidence. So we look at the similarity between vision and context, and only if that scores above a certain result do we push them up. We don't look at the individual item similarity confidence in each case. But they're still in a ranked order, so the ranking is based on confidence in the individual domains. But we did look at doing a voting system where each domain is an expert that votes based on its confidence. But actually, that didn't give us anything better than this rather simplistic measure. Cool. Okay. So, these are great questions, but it means we're probably only going to get through a quarter of what we're going to cover, but that's totally fine. So what did we do here? Well, what knowledge was used? Well, there's similarity of semantic concepts. It was represented using a distributional semantic model, in particular the Nassari model. And we used it to produce labels that humans could pick for unknown objects. So we're now able in this pipeline to go from objects we've never seen before to a 3D model of that object plus some labels for it. So in the next step, which I'm going to rush through, we're going to go into a bit more detail. How can we use the object labels plus the spatial semantics to do better recognition? So in our project, we've been using a lot of qualitative spatial relations. The idea of qualitative spatial relations is they capture the knowledge like this, that keyboards are often in front of monitors, mice are often to the right of monitors. And these qualitative representations allow us to capture and compress quantitative states into a single qualitative state. They often have built-in semantics, so people like them because it allows you to hand-code domain semantics very easily and allow kind of machine learning approaches to leverage that, or reasoning approaches to leverage that, but in still a reasonably general and well-founded way. And these relations are often relational. So they're usually qualitative spatial representations, but often we use relational qualitative spatial representations. And relational information is very powerful in reasoning. Some quick examples. We've got a distance calculi. So here you would say something is at distance 0, 1, 2, or 3 if it's in one of those rings. You can think of an angle calculi that tells you that something is at relative angle 0, 1, 2, or 3. And you can see this is capturing both these things. So we're compressing all those points there into a single logical state, which is distance 2, rotation 0. You can think of this as a logical abstraction. If you're more of a machine learning person, you can think of this as just a feature. So these qualitative states become features in some machine learning problem. There's lots of different ways of thinking about it. We wanted to do this kind of work on desktop objects. So we wanted to get a data set of desktop objects to compute qualitative spatial relations over. So in the Strands project, we produced a few of these. One is lots of images of desks in KTH. So this is KTH 3D Total. Whoa. Sorry, my laptop has just decided to be silly. Let's hope it doesn't do it again. And the other one is based on a more kind of qualitative assessment of qualitative spatial relations, where we just went around a bunch of desks and asked an expert annotator to tell us what relationships existed. So in the top case, you've got 3D models and point clouds. In the bottom case, you've got a human sort of psychological model of space, effectively. They're saying things are left. Okay, hang on. Is my laptop trying to reconnect to EduRoam for some reason? Okay, so what can you do with this information? Well, the first thing is you can look at object presence probabilities. This isn't a qualitative relation, but it gives you a prior for reasoning later if you're trying to recognize objects. So this is the probability of finding a particular object on a desk. Monitors are very, very probable. Hole punches in this digital age, particularly in computer science departments, are very, very unlikely. We represented then the relational information using something called ternary point calculus. In this case, you've got someone observing a landmark object and a target object, and you express the calculi as some coarse categorization over the angle and the distance. So this would be behind and to the left of. Okay, the target is behind and to the left of the landmark based on this angle and that distance. So this is one type of relation. There's many, many out there in the literature. And if you look at all the data sets that we had, so for example, that KTH 3D total, you can compute lots of probabilities of the existence of relationships. So in this case, you can imagine each one of these is like a feature describing the existence of a particular object in relation to something else. Or you can think of it as dictating the likelihood of its location. So here we could say that keyboards are typically in front and close to monitors, but they're not always that case. So they're never behind, but sometimes they're to the left or to the right. Sometimes they're distant and not close. That's really good for giving us a qualitative understanding. To do work in robotics, we often want a quantitative or a metric interpretation of this kind of structure. So to do that, and in the interest of time, I'm just going to kind of show you pictures rather than talk about the approach. We used Gaussian mixture models where we fitted a different mixture, a different Gaussian, to each of the relationships. And that gave us a way of combining different relationships, but in a quantitative and uncertain form. So this shows you the position of a cup relative to a monitor. So redder is higher probability. And so over here, you're much more likely to find a cup if you know where the monitor is, and you're not very likely to find it down here. You can think about the position of a cup relative to a keyboard, and you can see that a cup is much more likely to be in different places around a keyboard than a cup is relative to a monitor. Of course, when you think about the fact that keyboards are in front of monitors, it raises interesting questions about what landmark to suggest when you're looking for things. And also whether these things are independent or not. Yes?
Can you combine those two to say what is the likelihood that the cup is between the keyboard and the monitor?
Yes, you can combine the two. It wouldn't look like a combination of this. You would build a model from the subset of the relationships that are relevant. So then effectively you would end up with something that is I've lost my clicker. So probably stuff that is high probability in both, you would just end up with something that's there.
Does this also mean that you have added orientation of each 3D model? What is the front of the monitor?
That is the big question. So in this case, we're assuming everything is done relative to an observing point. So the origin is hugely important. And in this, we assumed a fixed origin, which was the place where the robot would stand. But in general, I'm not a huge fan of this calculi because of that assumption. So I think you could do interesting things where you have to effectively infer jointly the spatial relational graph and the observer position. So you know that effectively, if there's a monitor and a keyboard, you should be stood here to see the front. Yes? So that's another great observation. So a lot of this stuff, this is kind of dictated by the statistics you observe. I think in our data set, we had no left-handed people. So we didn't get anything interesting like that. We've only got mice on the right. But yeah, you would have a possible world, if you observed it, where once you see that a mouse is on one side, the coffee cup should be on the other. So that's the kind of stuff we'd love to come out of this work, but in our data, we weren't able to find it. But you want your inference mechanisms to have that kind of power, for sure. Right, I'm going to move on very quickly, otherwise I'm going to miss my flight home, which would be sad for me and my family. Maybe less sad for them. But so what do we do with this? Well, our robot spends a lot of time looking at scenes like this, trying to understand everything that's in them. This is clearly a fake scene. This is the robot lab in Birmingham. Nothing is ever that messy, that tidy on any desk of a computer scientist. And when we do this and we run, again, off-the-shelf vision algorithms, we get different results for each object, typically different results over time. So a mug is quite easy to spot. This thing here, which I think is a book, could be a notebook, could be a monitor, because it's flat and square. Could be a keyboard, could be a cell phone. So actually, vision is pretty bad at giving us a single label that we're confident in, again, in these noisy, challenging, robotic, real-world situations. So what did we do? Well, we did the thing we talked about earlier on, which is we used the spatial semantics to capture the relationships between these objects. So keyboards are in front of monitors. So if I know where the monitor is, I should be better at spotting the keyboard. And we did this, so we trained those Gaussian mixture models on 19 desks, and then we test on one desk, and we did this with k-fold cross-validation, where we trained on every possible set of 19 and tested on every one. I leave one out, validation, in fact. And the results look like this. So what we're trying to do is accurately predict, accurately classify every object in the scene. Okay, so we're trying to put a label in the scene you're given. How many labels can we label correctly? And this is averaged over all the desks we tried. So if we just use vision, so this dark blue is just using vision, we get a success rate. We label about 60% of the objects correctly. Okay? Then if we put in some learnt metric relations, so in this case the Gaussian mixture models that I showed you earlier, and we use those models to refine the hypotheses of vision, much like you saw earlier with the context. But in this case, we're actually using, there's two ways we've done it in this paper, either Bayesian reasoning, where we're looking at the probabilities of finding these objects in this position, or we've used voting schemes, where each relationship becomes an expert that votes for a particular outcome. Either way, we get a big increase in success. So we get to jump up to 96% success rate. This jump was so big and we're so happy about it, we thought, do we actually need vision? And it turns out you don't. So the light blue is what happens if you take away vision and only use the space. So in this case, vision is doing the segmentation for us, but then we just do the labeling purely based on the spatial relationships, then we get almost as good just using space. So this is a lovely result. The caveat is we're really looking at a very constrained world. We're looking at right-handed people's desks, effectively. So therefore, you would expect your inference to work well, but still it's a nice result. It shows you don't need vision, which makes me happy, as you saw from our earlier results. And in the paper, you can see we tried a range of different calculi to show which ones captured different amounts of information. And it seems that actually you need angle, distance, and relative size to get up here. So this is not just using the angle and distance. Once you put relative size of things, it becomes really useful. So there's a range of things that you can build that you want to capture from a scene to do this kind of semantic labeling. So what this shows you is that spatial semantic information is really, really important in a range of robotics tasks. And so we're actually, the key thing here is we're using qualitative structure to learn models that we could then use for kind of quantitative probabilistic tasks. We did that with a mixture of hand-coded QSRs and Gaussian mixture models. The details are in the papers, again, and we use this to improve a robot's ability to semantically label a scene. So I'm going to skip the whole thing about people and actually, no, I'm not. Yes, I am. I'm going to show you one slide as a kind of teasing open question and an advert, which is, so this is an image from our 60-day deployment in Milton Keynes. And I've shown you what we can do with objects and semantics. Well, this is now people and space, and it's equally interesting. So every greeny blue line there is a track of a person, and we have 11,000 tracks of people over 60 days moving through this space, okay? We've also got 38,000 instances of robots traversing an edge in the graph. So we call those navigation experiences, but there we record probability of success and failure, distribution over duration, how long was the robot waiting at the door that you saw earlier, which is here. And there's lots and lots of exciting information there that you can capture and do learning with in a similar way that I showed you previously, doing semantic stuff, doing clustering, doing qualitative spatial representations. And we've done a few things on that, which I'm not going to talk about now, because you've been such a wonderful audience and asked so many questions, which is great. So I'm going to jump very quickly to the summary slide, which summarizes both parts, but I think I kind of captured it already in the summary of the last bit of object work, which is what is in common everything we saw. Well, we're using abstractions to capture some of the semantics and structure in an environment. And typically, we're building those abstractions ourselves or building methods that are biased to find the abstractions we think are important. And that helps guide learning over real robot data. So given not a huge data set, not a kind of deep net level data set, but a big data set, of very noisy partial observations of people or objects, then you need to give your machine learning and your representation systems a hand, and often finding the right feature set, whether that's qualitative representations of space or something else. Finding the right feature set really gives you a hand. What you also saw is something I said at the beginning, and Patrick said, I'm not someone that's completely wedded to support vector machines or CNNs. I think if you work in AI and robotics, you have to be open to different ideas, whether that's probabilistic reasoning, whether that's regression, whether that's Markov decision processes. There's a whole space of things you need to learn about and apply them when the time is right. And in general, the applications are all about finding structure in real environments so that robots can get better at the tasks you want them to do. So the big answer to where can I read more, I encourage you to all go and read this paper. So this is our summary paper of the project. It's got lots and lots of authors because lots and lots of people have contributed to all the work you saw previously. It summarizes a lot of our results. It links to a lot of the papers you saw there. It's going to be published in Robotics and Automation magazine sometime in the future. We're not sure where, but the open source download is there. Also, all our data is online. So if you want the people trajectories, if you want the images, if you want the 3D meta rooms, please give me a shout or Patrick a shout or look at our project website. The other thing I'd like to do is thank all the people on this slide. So this is the Strands project, who are all super awesome and gave me really interesting things to talk about. And then at the end, I'd like to thank you all for listening, and thank you again for the invitation. Cool. So I'm happy to take like 5 minutes of questions, and then we can run to the taxi. That's... Yep.
The robots are moving around and you're getting this image in some frequency.
Mm-hmm.
So how often are actually you're running your kind of machine learning algorithm to identify the image? Because I would assume these are not also very compute intensive. So it requires some time, so your robot should maybe wax little bit, stop, sense environment, send a request somewhere.
Yep. Okay, so the question was, how often do we run these kind of recognition processes? And actually, we don't run them all the time. So we run 2 or 3 different types of processes. One, when we do the object learning, so the robot scans, then sees the object, then drives around it. So we do all the data gathering in real time, and then we do the model fusion offline. And then that just gets kind of stuck on a server, and then we do the generation of object suggestions. So that's happening in parallel. A lot of the other learning we do overnight. So for some of the clustering and classification work we've done on person trajectories, the robot spends the day observing people and then builds a new model at night, which it uses the next day. And that's also true for some of our other predictive work. So we tend to do data gathering and recognition using yesterday's models, and then we do the machine learning overnight. Any more questions? Yep. So the stuff we've done is mostly kind of unsupervised clustering type approaches, which run, and we run for a fixed window typically, and then we stop. And actually, the thing that we really like, or I really like, and that kind of traditional computer vision and machine learning people don't like, is that they don't know how good the answer is. Whereas I'm happy that the robot should get better over time. So often when we've done these approaches, we don't know how good our models are. So we do one thing where we learn predictive models for edges for navigation. And very early on in the robot's life, these things are awful. And the robot takes very, very weird paths through the environment because it thinks those are the best paths. We do have some exploration built in, so it gathers more data and ultimately gets better. But I quite enjoy the fact that you see the robot going very strange ways around the environment because it shows it's learning, even if it's doing something that's a bit crappy right now. So yeah, things get long-term, they get stuck in bad places, but they move out of it as they gather more data and more experience. There was a question back there, and then I'll come down. So in all the work we've done, we've used a 2D static SLAM map for the robot's position. In that case, we get plus or minus 5 centimeters accuracy. For the vision work, when we've got that 3D scan, the 3D scan is grounded in that map. But then over time, we do bundle adjustment and things like that, ICP and all sorts of that vision magic that I don't really know very much about, to match the images in a lot greater detail. So actually the final images we get when we're doing model building are matched against that meta room structure, so there's a much better accuracy from that, and that comes from having the long-term observations of the space. So in general, we're kind of plus or minus 5 centimeters, but for specific tasks, we've got lots of data, lots of 3D data in that area, we can get to much better resolution. Yep. So, yeah, so the question was, do we consider temporal information? So where you find the banana. You're much more likely to find, sandwich boxes at lunchtime in the kitchen and sandwich boxes full or, empty in the afternoon on desks. So that's what we're working on right now. So in fact, Patrick's group here are building a big database that supports observations across long periods of time, which we can query for point clouds and semantics and all sorts of things. So we help to be able to bring out those patterns discovered over long periods of times and then do that kind of work. So actually you change the probabilities of recognition, change the priors effectively based on where you are and when you are. Okay, okay, final question. Yeah, so deep learning is interesting for us. We can see that it's starting to kind of eat up the rest of the AI and robotics world, so manipulation and vision, for example. The interesting thing for the things I'm really interested in happen online, and it's about the robot adapting over days and weeks in an environment. So we do have lots of data, so if there were good problems, we could train on all loads of data, but we don't have annotations. So a lot of what we're doing is unsupervised. So we need to look at these big data kind of unsupervised methods. We have tried to do some work where we convert I give away one of my secrets now. So we've not got very far in this, but I think it's a great idea. We take the local cost maps of the robot, which indicate when the robot's been in collision, and we've tried training some CNNs based on the cost maps to give you predictions of when the robot's going to collide with things earlier than your navigation system does. We haven't got very far on that, but that's a great example because we do have a training signal built into the robot. So if the robot does collide, we can step back a few steps and say, well, this was the layout of the environment and my navigation plan before I collided. Can I build a kind of a CNN-type classifier on my local map data from that? So it's something we're interested in because those methods clearly work, but actually for a lot of the things we're looking at, we don't have enough supervision signal to match the volume of data we've got.